Hello everyone, welcome to Abhijit Codes. So in this video, we're going to solve a problem, minimum cost to connect all points. So first let's read the problem statement. You are given an array points representing integer coordinates of some points on the 2D plane where points at I equals xi comma yi. The cost of connecting 2 points is the Manhattan distance between them. Now, what is the Manhattan distance? So, Manhattan distance is nothing but the absolute difference of the coordinates of the 2 points. So, suppose let's take 2 points here 0 comma 0 and 2 comma 2. So, what will be the Manhattan distance between these 2 points? So, it will be x2 minus x1, and the absolute value of this plus y2 minus y1's absolute value. So, it will be 2 minus 0 plus absolute of 2 minus 0, that is 2 plus 2, 4. So between these 2 points the Manhattan distance is 4. Now what we need to do is we need to return the minimum cost to make all points connected. So if we focus on this statement, the minimum cost to make all points connected, this is nothing but the minimum spanning tree, and all the points are connected if there is exactly one simple path between any 2 points. So to solve this problem, we need to have the knowledge of minimum spanning tree. And if you do not know this algorithm, it's going to be very hard to come up with your own algorithm to solve this problem. So let's see one example here. So in the first example, they have given some points like this, and the result will be having these edges as the result. So we will take cost 9, cost 3, cost 4, and cost 4, and this will give us the minimum spanning tree, or you can say give us the minimum cost to make all points connected. So let's take one example to see what a minimum spanning tree actually is. So suppose we have certain points like A, B, C, and D, and there are some edges between them. So let's connect them like this. Now also give us, they have some weighted, so let's give them some weight. Let it be 5, let it be 9, 8, 10, or you can say 6 over here. So how does this algorithm works? So to solve this, to get the minimum spanning tree, we are using here Prim's algorithm. So let's see how this algorithm works. So in this algorithm, we first need to take any arbitrary edge, or can say node. So let's suppose I'm taking A here. So we take any arbitrary edge, and we need a queue. So let's define, let's it be a queue here. We get all the nodes connected to it. So C is connected to it, and the distance is 9. D is connected to it, and the distance is 10. B is also connected to it, and the distance is 5. Okay. Now when we are getting the edges, we will store them in a minimum min heap. Okay. So what is a min heap? It is basically like a queue data structure only, but it keeps the minimum value at the top of the queue. Okay. So after we add all these values, our heap will have something like 5 comma B. So we keep the weight first and then the edge, or you can say then the node. And next value will be 9 comma C. Then we'll have 10 comma D in our priority queue. So we take out the minimum value from the priority queue. Okay. So out of the three options available, we choose the one with minimum distance. Now A and B are part of our MST, minimum spanning tree. So we also need to keep all the visited elements. And here the visited elements are the ones that have become the part of the minimum spanning tree. So we will have something like MST, in MST, or not in MST. We can use a simple visited variable for this. So now the B has become a part of it, and as we have already processed A, so it will go out of the queue. Now we take out the front, and the distance we required, we will add it to our answer. So our answer becomes 5 for now. And now we'll try to get the all the edges from the B. So what are the edges from the B? There is only one edge that is not processed yet, that is from B to D. So from B to D, we see the distance is 6. So it will store 6 comma D. So we see the 6 comma D is the minimum, so it will come in front of the queue. So 6 comma D. So this will be taken out next, and the weight of this will be added. So our answer becomes 5 plus 6. So we have included D also in our minimum spanning tree. So now our minimum spanning tree has A, B, and D. Now we check all the paths we can go from D. So there is only one path from D, and that has weight 8. Okay. And at this point, we need to remove also the visited points. So D is visited, so we will remove this from our queue. C is not yet visited, so we will push 8 comma D in our priority queue, and this will pop out. This was already processed, so for the next we will have it added to our answer. And now 8 comma C, sorry, this will be 8 comma C, and C will also become a part of our MST. So to summarize this, what we see is, out of any graph, we first take a simple node, then we go to all of their edges, and we take the edge with minimum distance, and now it becomes the part of our minimum spanning tree. So in this case it was this, so now this is the minimum spanning tree. Next we again take out the minimum from the PQ, and again go to this its edges or adjacent elements, and next again we see the minimum edge, and we include this in our MST, and now we check all the edges, and finally we get all the elements included in our MST. So if we see the example, so for this we have cost 9, and this will also have cost 9, sorry it's 3 comma, so 8 plus 1 10, this will have cost 10. Okay, again this, and this will be having cost 7, and this will be, so we need to connect everything with everything else, so it will become a mess. Therefore I have not taken this problem. So in this way we can solve this minus finite tree problem using a Prince algorithm. So now let's see how to code it, and there it will get more clearer. So what we require is, at first we require some variable to store our answer. So let's say interest equals 0. Then also we need to check the number of connected points in our MST. So for that we say none, and it will also be 0. Then we need something to traverse this points vector. Okay, so this will be also starting from 0. Okay, and we also need some visited vector. So let's define vector bool visited. Its size will be, let's define here, int n equal points dot size. Its size will be n. The value will be false, as everything is not unvisited at this moment. Next, what we need is, we need a min heap priority queue. So we'll define priority queue, and we will have a pair of priority queue. And the first node will be used to store the weight, and the second node will be used to store the edge we are pointing to. So it will be parent vector of pair greater parent int eq. Okay. Next, we will traverse this while, now it will traverse all this pq. So while our, now, or let's call it connected points, connected, or MST size, you can say it, MST size. So while MST size is less than n plus, because at the first time we are having 0, we are starting I from 0. It means we are starting from the first node itself. Okay, what we'll do, we'll first mark it visited. So visited at I equals true. Then what we'll do, we'll go to its neighbors. So for int j equals 0, j is less than n, j plus plus. So in our case, every point can be connected to every other point. So we need to traverse every point from this current point. Okay, except, so first we'll see if not visited j. So if this point is not visited earlier, then only we need to take this into account. So if we had 0, we need to go to every other point. So first, two, second, third, all the indexes, and there we will get the Manhattan distance. And how we will find the Manhattan distance? So let's suppose we have int dx, change in x. It will be absolute of points at j and 0. That means the j points x coordinate minus points at I, 0. That means x coordinate of the point I, and its absolute value will be change in the x. Similarly, int dy will be the absolute point change in y. So we'll do like this. Now we need to push this value pq dot push dx plus dy. This will be our distance. And what will be the node here? The node will be j. So we are pushing all the connected nodes to I with their distance. And distance we are keeping it first because we need to extract the minimum element first. So with this loop, what we are doing is we are going to all the neighbors of I, and if they are not visited, we are adding their distance with j with their node. Now what we'll do, there can be case that that node becomes already a part of MST, and we are and it has not come out of the queue yet. So to handle that edge case, we will do while visited at I. So we will have the access of top. So we will see while visited pq dot top dot second. So there is the element where we have stored our. So if the top of the pq is already visited, we don't need to visit it again. Okay. So in this case, what we will do, we will simply pq dot pop. We will pop this top element if it was already visited. Next, we need to add the value to our result. So what we will do, we will do res plus pq dot top dot first because there is the weight stored here. Next, what we need to do, we need to change our I. So in the next step, first we are pressing 0, and now we have connected all the components to that are connected to 0. So now we'll select out of the all connected elements the element with minimum distance, and we will add that distance in our result, and now our I will become that node. So I will become pq dot top dot second, and then we'll simply pop this element out pq dot pop. At the end, we need to return this result. Let's see if it's running. Okay, sample test cases are passing. Let's try to submit it. So it is getting accepted. Okay, now what can be the time complexity? So here we are using a vector wasted, and in the while loop we are only looping till the maximum size of n. So this will run for big of n, and inside we are going for big of n again. So at maximum this can go till big of n square. Okay, and what about the space complexity? The space complexity will be just big of n used to store the visited vector. So time complexity is big of n square, and the space complexity is big of n. So thank you. See you in the next video.